All right, everyone, so today we're going to talk about transformations of functions. In this lesson, you're going to learn how to identify shapes of common functions, how to use transformations to change the position of a graph, how to shift a graph vertically and horizontally on a Cartesian plane, how to reflect a graph across the x-axis, and how to write equations to represent these transformations. First of all, we're just going to talk about some common functions. Right? The first common function you see here is the identity function. Common functions can produce what's called a family of curves, each with the same shape, but they are located in different places on the Cartesian plane. So we're first going to talk about their shapes for the next few slides, and then we'll talk about what we can do with it. So this first function is the identity function, it's just a linear line, a straight line. All linear functions are some form of the identity function. The next common function we're going to talk about is the squaring function. The shape of this graph is known as a parabola. All quadratic functions are some form of the squaring function. Quadratic functions we'll talk about in the next chapter. And then we have a few more. A cubing function, y equals x cubed. And the square root, y equals the square root of x. And then just a few more after that. Cube root, the reciprocal function, and the absolute value function. And so we're going to use all these functions, and we're going to use transformations to move these functions around on the Cartesian plane. So the first thing we're going to talk about is a vertical translation. To shift a graph up or down on the Cartesian plane, you want to add or subtract a constant to the function. Okay, we're going to add a number to the outside of the function. We're going to talk about what that means in just a moment. So for example, if we're given the graph of f of x, then if we had, say, f of x plus 2, that would shift the graph up 2 units. And if we had f of x minus 5, that would shift the graph down 5 units. This happens because every value in the function is moved up or down by the same amount. So if we have the graph of f of x and we add 2 to it, we're adding 2 to every point along that graph. And so the entire graph just shifts up by 2 units. So let's try this. Given the graph of y equals x squared, that was the squaring function from a few slides ago, we want to graph the following. Well, y equals x squared, it's going to look something like this. Y equals x squared. First thing we want to graph is y equals x squared minus 2. So that minus 2 just means we're going to shift every point on the graph down 2 units. So we're going to shift it down 2 units, so every point is going to be moved down. And we're going to get the same picture, just shifted downwards. Similarly, if we want to graph y equals x squared plus 3, now we're shifting the entire graph up 3 units. So it's the same picture, but now it's shifted upwards. And finally, we don't have to always use y, we can use f of x. If we have f of x is equal to x squared minus 5, that's going to take the same picture, y equals x squared, and shift everything down 5 units. So our graph will look something like this. So by adding or subtracting a constant to the outside of the function, to the end of the function, you're just taking the graph and shifting it up or down. We can also move things left or right on the graph. It's called a horizontal translation. We want to shift a graph left or right on the Cartesian plane, then we want to add or subtract a constant to the variable inside the function. And we're going to say you're going to add a number to the inside of the function. And I'll show you what inside means. The signs of this translation are a little counterintuitive, right? Plus implies you're going to move to the left. Minus implies you're going to move to the right. And this is because what you're essentially doing is shifting the 0 point of the graph, and I'll show you what I mean by that here as soon as we work an example. So for example, if you're given f of x plus 1, the whole thing in parentheses, right? This is a function name, f of x plus 1. It's going to shift the graph to the left 1 unit. F of x minus 7 would shift it to the right 7 units. So let's try an example. Given the graph of y equals x cubed, we want to graph the following. So we know y equals x cubed looks something like this. This is y equals x cubed. So that's our common graph that we're going to work with. First, we want to find x minus 3 cubed. Well, this graph is going to have the same shape as y equals x cubed. But that minus 3 inside the cubed, notice it's inside the cubed part of the function. That minus 3 is going to tell us to shift to the right 3 units. And so our graph will just be shifted to the right. Now, I told you the signs were counterintuitive in that minus meant to the right, plus meant to the left. And the reason is because you're shifting the 0 point. If you look at y equals x cubed here, when x is 0, y is 0. But if we shift it to the right, here, x is 3, but y is still 0. So we're shifting it to the right. If we had moved it to the left to minus 3, and then plug that value in for x, you would not get a 0. So now we want to try the next graph. We've got g of x is equal to x plus 4 cubed. And so that plus 4 just means we're going to shift to the left 4 units. So the same picture, but shifted to the left. Notice we shifted that 0 point. So that negative 4 plus 4 is 0. Finally, we can combine these horizontal and vertical translations together. So our last function, h of x equals x plus 1 cubed plus 2. X plus 1 within the function on the inside of the cubed part tells us that we're going to go to the left 1 unit. And then the plus 2 on the outside tells us to go up 2 units. So we're going to start from our 0 point, and we're going to go to the left 1, and then up 2, and here's our new 0 point. And so there's our new graph. Same picture, just shifted to the left 1 and up 2 units. So the last thing that we're going to talk about is reflection across the x-axis. If you make a function negative, then it'll reflect the graph across the x-axis. Essentially, the picture just flips over. So what you want to do when you're graphing these things is to first shift the 0 point, and then invert the picture. So move to the left and up or right and down, or move in the proper direction for the horizontal and vertical translations, and then just flip the picture over. So for example, we were given the graph of y equals the absolute value of x. And y equals the absolute value of x looks like this. If we make that negative and say we want to graph y equals the negative absolute value of x, then it's the same picture just reflected across the x-axis. So the picture itself just flips over. So if you put a negative in front of the function, it's just going to flip the picture over. So we can put all this together, right? All the transformations can be used to determine many families of graphs. All these graphs are related by their basic function, by their common function. Other graphs can be made by multiplying or dividing by constants. This will stretch or shrink the graph horizontally or vertically, but we're not going to talk too much about this at all. And you can use the 3 possible transformations to determine what the graph will look like. So for example, now we want to graph f of x is equal to minus x minus 1 squared plus 3. If we look at this function, hopefully you can see that the base function is y equals x squared. It should look something like y equals x squared. However, there are some things that we have to do. The x minus 1 tells us to go to the right 1. The plus 3 tells us to go up 3. And the minus tells us to flip the graph over. So it's going to be the same shape as y equals x squared, except we're going to go to the right 1, up 3, and then flip the graph over. And so there's our new picture. Shaped like y equals x squared, but to the right 1, up 3, and then reflected across the x-axis, flipped over. Let's try another. F of x, 1 over x plus 2 minus 5. This is a reciprocal function. When you're dealing with a reciprocal function, the inside part of the function is the denominator. The outside part of the function is whatever number's on the outside. Okay. So this is going to look like y equals 1 over x, except we're going to shift it to the left 2, and then down 5. And now the reciprocal function is just a little different to graph, because the 0 point is actually not part of the graph. When you look at the reciprocal function, if you go back to a previous slide, the reciprocal function looks like this, y equals 1 over x. We're just going to take that function, shift it left 2 and then down 5. And so left 2 and down 5, notice once again that 0 point is not included in the graph itself. So we move the 0 point, but it's not going to be included in the graph. And so this thing should really be like this. Same picture, just move to the left 2 and down 5. Okay, let's try another. Y equals negative square root of x plus 3 minus 1. The minus tells us to flip the graph over. The basic function here is the square root, so we're going to use y equals the square root of x. Plus 3 on the inside tells us to go to the left 3. And then minus 1 on the outside tells us to go down 1. And so we're going to go to the left 3, down 1, and then we're going to flip the graph over. And it should look something like that. So you need to be able to write equations using these transformations, right? So to write the equations for functions, just follow the directions in the earlier slides, how to add in these numbers where they belong. For example, the right equation for a graph that has the shape of y equals x squared, but shifted to the left 4 units and down 8, we would write y equals x plus 4 squared minus 8. The blue tells us to go to the left 4, and then the red tells you to go down 8. If we wanted to flip the graph over, we would just put a minus in the front. The shape of the graph is given to you. It's the shape of y equals x squared. It's the shape of the overall function. So we want to be able to describe how the graph of y equals the cube root of x minus 1 plus 2. So y equals the cube root of x minus 1 plus 2 can be obtained from just y equals the cube root of x. Well, here's just asking for directions, right? What do we do? Well, the minus 1 inside the function, that's going to tell us to go to the right 1. The plus 2 on the outside of the function is going to tell us to go up 2. So the new graph would be the same as y equals the cube root of x, except shifted to the right 1 unit and up 2 units. And so finally, we should be able to write the equations of these functions, and we should be able to graph them as well. So we want to write an equation for a function with the shape of y equals the absolute value of x, but shifted to the right 3 and up 5, and reflected across the x-axis. So right 3, up 5, and then flipped over, reflected across the x-axis. And then we want to graph the function. Well, to go to the right 3, on the inside of the function, inside the absolute value, we're going to want to put x minus 3. Minus 3 will shift it to the right 3. And we want it to go up 5. So on the outside of the absolute value, we're going to put a plus 5. And then because we want it to flip over, in the front, we're just going to make it negative. And so it's y equals negative absolute value of x minus 3 plus 5. So we can use our directions to graph this thing. We know that it goes to the right 3 and up 5. Right 3 and up 5, here's our point. But it's flipped over, and it looks like the absolute value of x. And there's your graph. So at the end of this lesson, you should be able to identify some common functions by their graphs, use transformations to shift a graph vertically or horizontally, and to reflect a graph across the x-axis, and then to write equations for functions given these transformations.